Let's quickly go through chapter 5, paired samples. So chapter 5 is about some methods for paired samples. We will not introduce any new methods, but we will use what we have learned to deal with paired samples. So first of all, why do we use pairing? Or why do we have to pair two or more samples? We have talked about why we pair samples in statistics 1 and SPC. Now let's review the situations. We pair two data sets when each observation of the two data sets belong to one owner or have some ties, have some relations, or belong to one subset. For example, married couples in a community, or left and right feet or hands for multiple individuals. Or sometimes we have some performances for each individual before and after an activity, and we compare the before and after data to check if the activity makes a difference. Let's look at examples when we use these paired samples. So researchers wanted to know if people can perceive numbers with the same speed in the left vision field and right vision field. We got 12 volunteers. Here are 6, and here are another 6. And here are their response times in their left visual fields, LVF, and right visual field, RVF. And we pair these two data sets, the LVF for 12 people and RVF for 12 people. So we also use each person's LVF. I think the unit is in milliseconds to subtract his or her RVF response time to get a third sample here. This 1 minus 2 sample is just the differences between each person's left and right response time. So you may have noticed that for different individuals, their response times vary a lot. We have the slowest person who has a 580, and the quickest one, this is the quickest one, only 467. So for each person, his or her left and right response time varies very little, right? But for different individuals, they vary a lot. But when we do this pairing, when we paired these two samples and use these differences, we kind of don't consider the differences between individuals. We only analyze the differences between their left and right eyes, right? So I guess intuitively, most people's left response time is longer than his or her right response time, right? There's only one exceptional here. So intuitively, the conclusion may be people's left vision field's response time are often longer than right vision field. But scientifically, we need to do some statistical test to make this conclusion. So that's one situation when we need to use the paired sample analysis. There are some further examples of paired samples. For example, compare traditional lectures with computer-aided teaching. Yeah, so for this, personally, I don't like online teaching. There are no interactions, very little communications. But if teaching in person and just using some online methods, some computer aid, as assistance, that would be better, right? So, or two graders on the same axis to see if they have significant difference on the same assay, or testing two diets for twin labs. So the key for paired examples, for paired samples are we only need to compare the difference between these two pairs. In other words, other factors between these two pairs should be all the same. In other words, these two pairs should be comparable. So the differences between paired observations actually become a third single sample, right? So we usually use DI to denote the difference between the two paired samples of the ith atom. So which means we can use single sample methods that we have learned in chapter 3 and chapter 4 to analyze the differences between the two samples. So let's look at example 5.1. Using the data of the left and right vision field response time, assess if there is a consistent response difference between left and right, then find a 95% confidence interval. So we use DI to denote the difference between left and right for the ith person. So DI should be a random sample with independent observations, right? So this is a single sample problem again. So for sample DIs, we can use Wilcoxon test. The full name of Wilcoxon test is Wilcoxon signed rank test. So first we order the differences, the DIs, in the ascending order from the smallest to the biggest. Then we observe there are ties. So we use mid-rank rule to get their signed ranks like this. Using the sign test, the median is 0, should be 0. We want to test if the median is 0. There is 1 minus sign and 11 plus sign, right? And then if we use sign test to get exact p-value, the asymptotic p-value, the exact p-value is 0.0063, and the 95% confidence interval is from 7 to 22. This is sign test. If we use Wilcoxon test in R, then we can only get asymptotic p-value, right? Because we have ties in ranks, and Wilcoxon test in R can only give us asymptotic p-value other than exact p-value. These two p-values may seem vary a lot, but however, they lead us to make same conclusion based on this, right? And the asymptotic confidence interval is between 9.5 and 23.5. And if we use wash averages to get the median, it should be 17.25. So why do we need to use different methods? Because when we know that the data set may be appropriate for multiple methods, we can always use multiple methods to get results and compare the results, and then discuss why and how this difference comes from, and learn more about the features of our data. So after applying sign test and Wilcoxon, then we can get some observations, get some interpretations. Using a two-sided t-test, Okay, now besides sign test and Wilcoxon, we also apply t-test to the data because this data set may be approximately normally distributed, so we can apply t-test on it. But the confidence, the p-value, it's still very small, which make us reject the null. However, the confidence interval is much shorter than the other two, right? It's much shorter than sign test confidence interval, but it's slightly shorter than the Wilcoxon confidence interval. And so why do we get slightly different results using different methods? That's because of the nature of the data set. So we will summarize when should we use each of the methods, or under which situation one method may be more desired than other methods in the summary of this chapter. So anyway, based on our test results, there is strong evidence to reject the null because all p-values from all methods are very tiny. And then Lillefer and Shapiro-Wilk test, we didn't expand too much here. But anyway, due to the textbook, if we apply these two methods here, those two tests don't reject normality, which means using normal asymptotic results makes sense here for this data set. So every method indicates the same conclusion, which means the conclusion should be all right. And the median should not be 0. There is a significant difference between left and right response time. So next example, let's look at another application in a different field. And it's used quite often in education. 11 children take a pre-test and a post-test. We pair them to see if the tuition makes any difference. So 11 children take a test before a tuition and get a score. Each of them get a score. And then they take an extra tuition as a training. After that, they take another test, which is a post-test. And most of them, no, all of them got their scores improved. And now we want to test. We know they all make progress. So we want to test if their extra tuition helps them get, on average, 10 more marks, which means the median of this sample, the second minus the first, should be 10. That's our null hypothesis. So using signed rank test, we use each individual difference, or in other words, we use each deviation to subject 10, right? 10 is our hypothesized median. So those are signed ranks with ties. And then starting from 0 to the largest magnitude. And this is using the mid-rank rule to correct the ties. Then, given that we got the signed ranks using the mid-rank rule here, and then therefore we can calculate the S plus, which is using the mid-rank rule, we get the S plus as 19. So this is because we have 11 observations. The sample size is 11, which means 19 is a smaller number right? The S plus is smaller than S minus. So we use this smaller value to do the test, to run the test in R. And then we can get exact p-value and asymptotic p-value. So they are not the same. Using stat exact, we get exact p-value as this 0.248, and then using R, we can get asymptotic result, the p-value as 0.229. But they all lead to the same conclusion. We fail to reject the null hypothesis, which means on average, students all improved. On average, 11 students got their score improved by 10 points. So if we use R, because this is a two-sided test, we need to use 2 to time the p sign rank this function. And since we always get a +1 here, when S plus is 19, we need to calculate 20 here because this is a shorter tail, right? So we need to know the probability of getting a value lower than this. So we need to use 19 to +1, and this is 20. Or we can use Wilcox test in R and define the data set. We can just give the difference data set instead of the ranks or assigned ranks, and then give the hypothesized median here. All right, so based on that, we have some comments. The textbook made some comments as usual. There are some questions that we need to be aware of if we take the paired sample tests to evaluate the extra tuition. Usually we need to make sure the two tests, the two exams are comparable. Their level of difficulty are the same. So how can we do that since we only have 11 children? How can we tell if their pre-test and post-test are having the same level of difficulty? So in reality, some standard tests based on large groups can ensure the consistency of the level of difficulty, which means we have a lot of students take 2 tests and give some results that indicate the 2 tests are with the same difficulty. And we use this a lot in all the standard tests like SAT, TOEFL, GRE. Those tests are all based on large sample to control the quality of the test. So for this example, the nominal confidence interval using stat exact is very close to the asymptotic confidence interval using t-test. And not every individual can benefit from this one extra tuition equally, because of course, if the initial score, an individual's initial score is low, then he or she may benefit more from tuition than the people who already get a high score in their pre-test, right? So, so for this kind of exams, usually the upper quartile make little difference, and the lower quartile may make more difference. Okay, another interesting example, we want to compare the systolic blood pressure before and after exercise. So we have 24 out of 77 as a random sample, which means we have a 77 students group. But for this test, we only randomly choose 24 of them to as a smaller sample to perform the test. We want to get a 95% confidence interval of people's blood pressure changes due to exercise. And we apply multiple methods again. So we use the sign test, then Wilcoxon test, and then the t-test. And let's see their difference. Again, why do we need to use multiple methods? Because for this type of data, if for a data set, it doesn't indicate us that which method is not appropriate, then a better way to get more comprehensive results and interpretation of the data is to use multiple methods and let them verify each other, and then get more information about the characteristics of the data, whether they are symmetric or skewed or more like normal distribution or less like normal distribution, or have a long tail on one side, things like that. So that's why we use multiple methods. All right, so let's skip some of the details because those are the methods we have learned in chapter 3. So conclusion is, when we use sign test, the 95% confidence interval is from 15 to 40. Wilcoxon from 17.5 to 35, which is shorter. Using t-test, it's longer than Wilcoxon, but shorter than sign test. If we use R, here are the code. So pay attention, there is simple but clumsy method using R to identify sign test confidence interval, which is using the binom test. So binom test is here we need to try different number. We can change this number from 1 to n, increase 1 at a time. And here is the sample size, 24. And here is the p-value, which means from our 24 observation sample, what is the probability of falling to one category. So we can see that we have 2 minus, right, 2 negative value. And then all the other 22 are positive value, which means 2 out of 24 are minus, which means 2 out of 24 people get their systolic blood pressure even decrease after exercise. So that's the P. And then when we change this value, we can either manually change it and run this function at a time, or we can run a loop. Anyway, as long as the result is another p-value. Sorry, result is the confidence interval of the p-value. When that p-value just contain 0.5, that is the and this value here is the rank or the order of item as the bottom. As the lower limit of the confidence interval. Okay, let's go to R to see this. So let's go to R, binom, the test. Let's see, 1, 24, and P equals 2 out of 24. So then we get a p-value like this, but this is the p-value of when P is 2 out of 24. What's the chance? What's the p-value to get just the 1 negative out of 24? That is high. It makes sense, right? Because 2 out of 24 is close to 1 out of 24. But here we get a 95% confidence interval of the p-value of this p-value here, but this p-value is lower than 0.5. which means 1 is too small. We should not, our 95% confidence interval of how many observations cover 95%, it should not start from the first item. So let's see if we change 1 to 4. Then what happens is this p-value here is lower, which means if the probability of each trial is 2 out of 24, then the chance to have 4 negative out of 24 is this much, is lower, right? Then still, this range here does not contain 0.5. Then we need to increase this x here from 4 to, let's say, 6, which means we get p-value lower this time, right? The p-value of this p here. And then this confidence interval just does not contain 0.5, which means 6 is still small. Then let's change it to 7. So when we increase x to 7, this range can just contain 0.5, which means the lower bound of the confidence interval of how many items. So how many items in the middle covers 95%, start from the 7th, and the upper bound is from the 7 from the right. So the 7th item from the left, or the 7th smallest item, is 1, 2, 3, 4, 5, 6, 7 is 15. And the 7th largest item, the 7th item from the right, is 40. In that way, we identify the confidence interval. 95% confidence interval is from 15 to 40. That's how we get the sign test confidence interval using the binom test here. And Wilcoxon is simpler because we can just define confidence interval as true to get this 95% confidence interval. And t-test is using this t.test function, and we need to define data as this numeric vector, C parentheses, and then copy paste the all the samples, the differences between the paired samples here. Then define mu as 0 and confidence interval as 0.95. So we use 3 different methods and get 3 different confidence intervals, and they're relatively close, but still we may observe some discrepancies here. Why is that? So let's interpret about these differences here. We see that the sign test returns the longest confidence interval, right? And that's because there is a slight skewness. None of the intervals, where is the slight skewness? Let's say that it's from -5, -5, and then increase every time by 2 or 8 or 5, everything's normal. But suddenly we have a 80 and 85 in the upper tail, which is much, much longer, a really big step, really big leap versus all the other items. So this is slightly skewed towards the left, which means has a longer upper tail. And none of the intervals from the 3 methods is seriously displaced than others, although they may have some differences, but they all kind of close to each other. There's no big discrepancies, sudden discrepancies. One method is so different from all the other, right? And the Wilcoxon interval is the shortest because it's based on normal theory. but our data has a long upper tail. So the normal theory here is not very appropriate. And since we have a 77 observation group, if we use the larger group, maybe not all of the 77, but maybe not 24, maybe 30, 36, 40, we definitely have that data. So if we can use a larger group, our study may be more convincing. If we choose larger group, larger sample, we get the similar results, then our conclusion is more persuasive, right? And then interesting part is based on the result, and after they double check, after the operators of this problem double check their data collection and the calculation, they find an error in their data. After correcting that error, they refine their data, so they get another 3 confidence intervals using 3 different methods. This time, sign test and Wilcoxon seems all right, although this upper bound of the confidence interval vary somehow a lot, but t-test, the lower bound is too low, right? So which means for this time, the data is not that normal. It's not quite normally distributed. So t-test the result is kind of away from the other two. But how do we know that if one result is different than the other two? Is this one result wrong, or are those other two methods are wrong? So this this tied to design of experiment, and also we need some common sense help us analyze which type of the test is the most appropriate based on the data's characteristics, like if they're skewed, if they are normally distributed, and if they have a long tail. So then we can use more tests to help us verify the results. Lilleford test, Shapiro-Wilk test, and all of them returns the very tiny p-value. So which means for these 3 tests here, when they get a p-value closer to these 2, the results makes more sense. And if t-test's p-value is relatively farther away from these 2 p-values here, then its confidence interval makes less sense, right? So that's to have multiple methods to verify each other. All right, next, let's look at an example of a less obvious use of the sign test, which means when we get the data, we may not know that the data is fit for a sign test. But actually, we can use the sign test to analyze the data. This is example 4, example 5.4. There are 2 rock climbs. Mountaineering club wants to know which one is more difficult to climb. So here is the record of the members in this club for trying the 2 climbs. And it's summarized in this matrix. Some members succeeded in both climbs, some failed in both climbs, but some succeeded in one but failed in the other. And with this data, we want to test if one climb is more difficult than the other. So, although the data is not in the form of a vector with positive and negative value, but actually they deliver the same message in this way, right? The members who succeeded in both climbs and those who failed in both climbs, in fact, they do not tell us anything about the difference in the 2 climbs, the difficulty, right? So what we concern more is these 2 values here. the 14 and 9, because these two values, and by comparing these two values, we may know which climb is more difficult than the other, or they have similar difficulty, right? So we can let the upper right value here as the plus signs, and then the lower left as the minus sign, and compare this plus sign and minus sign. And the p-value is large, which means we fail to reject the null. The two climbs have similar difficulty. Using R, it's very simple because this is a two-tailed test. We use 2 to multiply the p by norm, this one, so this here altogether 14 plus 9, 23 people, and 9 of them failed in the second climb but succeeded in the first. So we use 9 out of 23 with p as 0.5. Then this, although 14 is different from 9, we still need to conclude there's no significant difference in the difficulty of the two climbs. All right, then power and sample size. We talk about this in SPC, but in this course, this is the first time we tackle about this problem, this issue, this topic. So we know that when we increase sample size, the power of a test can always be increased, right? But then we always need to determine the sample size to reach to a certain point of the power. We don't want the test, the data have as large as the power as possible. We have to stop somewhere. So here, this is an equation called Noether-approx that helps us determine, that tells us the mathematical relation between sample size and the power of a test and the significance level, and the P1, which means the probability of falling into one result out of 2 here. So because our course is more like a practical course than theoretical course, we skip the mathematical part. We just need to know the result of this approximation here. It's a good asymptotic approximation for power of a sign test given type 1 error alpha or confidence interval 1 minus alpha, and then probability of type 2 error beta, or the power of the test 1 minus beta. Given the probability of each of falling into one out of the 2 results, then what's happening? Okay, then if we want to determine how large the sample size should be to tell us a powerful enough result, then we can use this equation to help us determine that. Example 5.8 is given the value of alpha and beta, the value of beta, then using the using the normal approximation, we can get z alpha and z beta here. Then with the probability P1, we can determine the smallest sample size should be this one, right? Since sample size should be always an integer, we need to round it up. So we know that to reach a certain level of power of the test with a confidence interval, we should have 34 as the smallest sample size. All right, let's go to the summary or the field of application. So usually there are a lot of application fields of this paired samples. So let's first look at the summary of this chapter. We have used the sign test, Wilcoxon sign rank test, and t-test, which are always are already learned from previous course or chapters. We use them once again for paired samples here in this chapter. We apply all of them sometimes to compare the results, but there are situations that prefer one method than others. When should we use each of them, and when can each method give the best results? So usually, if the numeric differences between pairs are not skewed or more symmetric, then we would like to apply Wilcoxon test. If the differences are approximately a normal distribution, then t-test is appropriate. So even when each of the two paired samples are not normal, as long as their numeric differences are approximately normally distributed, we prefer to use t-test. Otherwise, if there is skewness in differences, we would prefer to use a sign test because sign test is robust to skewness. So then here are some fields of applications of those methods for paired sample. For example, to compare the lab instrument, the same instrument but from two brands, two producers, so we can use Wilcoxon test. And to get a confidence interval of the changes of some vitals before and after some activities like exercises or treatments, then we can use Wilcoxon confidence intervals. Other application fields include comparing two brands of a product, comparing two methods, comparing the effectiveness of education, training, and comparing people's salaries, etc. So homework 5 is due next Sunday, only 3 problems. I will adjust the weight of the homework based on their workload. For example, before I define each homework has a 10 score of your final score, but some homework they have 5 or 6 problems. I may make the weight a little bit higher than for the homework with only 2 or 3 problems. I may adjust its weight a little bit lower, so it will be more fair. And then let's go through homework 2. If you don't have any question on homework 2, you can skip this part. But for homework 2 solution, it's a very complete solution. It's not just the key. I just want to highlight some common mistakes. For problem 2.1, a permutation test, there are 2 ways. You can use the method in our textbook for manually calculate the exact p-value, which is you list all the probability, all the possibility, the combination of the ranks. Then you get the sum rank with the occurrences and then calculate the probability, or you can use asymptotic results, calculate the mean, sample mean, and sample standard deviation and get their z-value and use z-table to get the p-value. But anyway, you need to use the rank and the sum of rank sum instead of the exact measurements, right? Because permutation test is always using ranks or orders other than the real value of the measurements. And then problem 2.2, pretty straightforward. We already have that rank sum with occurrences table. We just need to look at identify the same probability. All right, and then problem 2.4. It's actually a two-sided test. Read the problem again and again. You need to find out it actually wants you to test if the median equals 2 to 5 or doesn't equal 2 to 5, right? So it's a two-sided test. Then 2.6. This time it specifies it should be a one-tail test. So you need to identify the probability of larger than or equal to a value, and when it covers 95%, it just covers 95%. We'll stop there. So the 10th item should be from the bottom, from the lowest value to the 10th item value should be the confidence interval, which is this one, right? Although the lowest value in the sample is not 0, however, the sample is quite discrete with very limited values, right? So theoretically, we can go even lower. The lowest value theoretically we can go is 0. So the confidence interval should cover from the lowest value, which is 0, to the 10th observation in that sample, which is 454. Okay. And 2.8, it actually is a problem asking you the cause of type 1 error, right? So you can think of multiple causes, may not just limited to these 3 here. Okay, that's all for this week.